Hi everyone, Chris Tisdell here. In this video, I'm going to continue my Beginner's Guide to Calculus series. And I'm going to look at the applications of derivatives. Now, in previous videos, we looked at the idea of a derivative, and we looked at limits, and we calculated a few basic derivatives. Now, this video is just a basic introduction to these sorts of things. I actually did a live stream video for this a bit earlier this morning, but for some reason there were some problems. So I'm going to just go through the notes quickly again. Okay, so in this section, we're going to learn about first and second derivatives of functions and how you can relate them to, say, the geometric properties of a function, or how we can use them to incorporate curve sketching techniques. And we're also going to look at some applied problems of maxima and minima. So just to recall, if you have a function like x cubed, then we know how to take the first derivative. Okay, you bring the 3 to the front and you change the power to, you decrease the power by 1, so x cubed will become 3x squared. For the second derivative, you just differentiate the first derivative. So the 3x, in this case, the 3x squared, well, the 2 comes to the front and you decrease the power by 1. So the derivative of 3x squared will just be 6x. Okay, so in one of the very early videos I did on this section, there was a link between the function's behavior and its derivative. So if you have a function on some interval I and the derivative is positive on that interval, then f is increasing from left to right. If the derivative is negative on that interval, then f is decreasing on that interval from left to right. And if the derivative is 0, then f is neither increasing nor decreasing. It's got to be constant, horizontal. Okay, so here are some basic ideas that we're going to continue this way of thinking regarding concavity. So this is a definition here. Basically, concavity is connected with how a graph bends or turns, and that's going to be really useful for graphing functions. Okay, so function f is concave up on an interval if the derivative is increasing on that interval. Okay, we're talking about the derivative increasing here, not the function. A function is concave down on an interval if the derivative is decreasing on that interval. Okay, so here I've put in an example. I've just used the basic function x squared. Where is this function concave up and where is it concave down? So I've taken a very geometrical approach. I've drawn in the graph of x squared, and then I've plotted some of the tangent lines. So you remember that the slope of the tangent line is the derivative at a point to the curve. So you can see here the slope of these tangent lines is increasing. It's highly negative there. It's less negative, less negative, less negative, 0, then positive, positive, more positive, positive, positive. Okay. So as we move from left to right, the gradients of the tangent lines are increasing. So just from the graph, we know then that as we move from left to right, the derivative is also increasing, not just for some values of x, but for all values of x. So in this case, the function x squared is concave up for all x in this interval, all real numbers x. Now you could do it another way, saying alternatively, if I calculate the derivative, where is this function increasing and where is it decreasing? Well, here's the line y equals 2x. As we move from left to right, the graph increases. So again, for all x, this function, the derivative is increasing. So for all x, the function is x squared is concave up. Now we can also use the second derivative to examine concavity. Okay, so essentially it's the equivalent of these things here. So f dash is increasing, f dash is decreasing. Basically, you can recast that as the second derivative is positive on an interval, then f's concave up, and if the second derivative is negative on an interval, then f is concave down. So if we use this original function again, let's calculate the second derivative and see what happens. So x squared goes to 2x, and then the 2x will go to 2. So the second derivative is 2, which is always positive. And so again, we get the same conclusion. F is concave up for all x. Now, at the end, I just drew a little graph in and to show you that the certain functions can be concave up and concave down. So you can see here, say over this part of the graph, the derivative is decreasing, right? So on this interval, the f would be concave down, and then here will be concave up again. So this is a case. All right, let's have a look at the comments. Shingles, hello. Thanks for the shout out. Shingles says, thanks for all you do. I'm glad. Let me write something back. Thanks, Shingles. You're right. He says, been watching your channel for years. I've been doing this for 10 years now, Shingles. I know, I can't believe it. Thank you for all the support. And let me go back to what we're doing here, just to wrap things together. Concavity is connected with how a graph bends or turns. And you can either talk about a function being concave up and concave up by looking at whether its first derivative is increasing or decreasing, or equivalently, you can look at the second derivative and see whether that's positive or negative. You can use graphical techniques like I did here, or you can use algebra and inequalities like I did down here. All right, thanks for watching, everybody. If you have any comments, any questions, please put them in the comment section below. All right, guys, all the best. Bye.